So we continue our discussion of integral extensions by proving, so the next statement that we want to prove is the following, called the going up theorem. There is a similar going down theorem also, which we will not prove now. Towards the end of the course, if we have time, we may consider it, but it is, so that depends purely whether we have time or not. And it's also not, I mean, we will try to develop things that are of use in computational situations. Okay. So recall our setup is that R inside S integral. Okay. Let P0 inside P1 inside up to PL, so a chain of primes of length L be in spec R, okay, and Q0 in spec S such that Q0 contracts to R to P0 in R. Okay. So we can think. Let me finish the sentence. Then there exists Q1 dot QL in spec S such that QI contracted to R is PI for all 1 less than I less than L. Okay, so we can think of it as follows. There is an integral extension R to S. Okay, and then there are primes here. Primes here, and then there is a prime here contracting to this. Okay. So in other words, the map of spec Q0 is in the fiber over P0. Then the theorem asserts that there exists a Q1 and similarly there exists a QL contracting to this is there exists spec such that there exists Q1 through QL such that this, and they form a chain, Q0 inside Q1 inside QL. So this chain goes up as a chain like this. Okay, so that's why it's called a going up theorem. So here is a chain of primes. There is a prime which is in the fiber of over this smallest one. Then this chain can be lifted to in spec S. Okay, so this is what okay, that's what this theorem says. Okay, so let's prove this. Okay, so if we have to prove this, we can just prove for L equals 1, because if we can extend this, then we will get a Q1. Then between P1 and P2, apply the same theorem to get Q2, because Q1 has already been obtained. So now Q2 has been obtained, so now apply that to P2 and P3 and so on. Okay, so one would get a chain of primes this way inside spec S. So without loss of generality, L equals 1. Okay, so this is, rest can be done by induction. Okay, so this is the picture. So let me just repeat the picture that we have here. This is the integral extension. Then there is a P1 containing P0 here and a Q0 mapping to this P0, contracting to that P0, and we would like to construct something here. Okay. So go modulo P0. Okay. So then we have R mod P0 inside, and inside here we get P mod P0, and then we have S mod, R mod P0, go mod P0 in R and Q0 in S. So we just get, okay. So this is integral extension, that's the point. And in this situation there must be something here. So there exists a Q prime ideal of S mod Q0, okay, there exists a prime Q prime like, okay, such that Q prime contracts to P mod inside R mod P0, R mod P0, it contracts to P mod P0, okay. But then any prime of Q, any Q prime which is of this form, so this one will give a Q1 in spec S. So here it's a prime ideal of S mod Q0, okay. Q1 contains Q0 and Q1 contracted to R would be P1. So such a Q prime will give a Q1, its preimage would be would have this property and this. Okay, so this is the going up theorem. Okay, so now let's try to understand these things in terms of dimensions. Okay. So, corollary, dimension of R equals dimension of S. Again, same situation, R to S is integral. Okay, so proof. So we have to prove that supremum of lengths of chains of primes in R is equal to supremum of lengths of chains of primes in S. So we will prove that for each chain here, there is a corresponding chain, there is a chain of the same length on this side, and then the other direction, and then when we take supremum, this will be fine, and we will prove the two inequalities this way. Okay, so let's just first prove that dimension R is greater than or equal to dimension S. Okay, so let Q0 inside Q1 inside QL be in spec S. Okay, so supremum of such L is what would give us this dimension. This implies that by the incomparability theorem, which is part 2 of the earlier proposition, Q0 contracted to R is distinct from Q1 contracted to R, QL contracted to R, which means any chain that we pick in spec S, there is a chain of at least that length in spec R. Okay, so now this implies that dimension of S is less than or equal to dimension of R. Okay, you can pick any chain here, you will get a chain of equal length here. So the supremum of all such L will be less than or equal to supremum of lengths of chains of prime ideals inside spec R. Okay, so this is this direction. So this is real. This is so this was 2 of the proposition. The statement what we called incomparability. Okay. Now for the other direction. Okay. So let P0 up to PL be a chain of primes in spec R. Okay, by lying over Okay, this is part 3 of the proposition. There exists a Q0 such that Q0 contracts to P0. So going up theorem doesn't assert the existence of Q0. It assumes for every Q0 mapping to P0, there is a chain that begins from Q0. Okay. It is lying over which asserts that there is such a Q0. By going up, okay, we get a chain Q0 inside Q1, QL, such that Qi contracts to R to give Pi, okay, for all I. Okay. So now this is the same argument. Given any chain inside spec R, there is a chain of at least that length in spec S. So this now implies that dimension of R is less than or equal to dimension of S. Okay. So therefore this is equal. Okay. So now we would so far the only concrete integral extension that we saw, or sort of sufficiently general, was Noether normalization. So this one now says that given a finitely generated algebra over a field, there is a map there is a map from a polynomial ring, finite map. So if you look at the map in spec, it is surjective, and these two rings have the same dimension, and hence we should know a way to find the dimension of a polynomial ring. Okay? But as I mentioned earlier, it would take us a little bit of work to prove that statement, that it is equal. Dimension of a polynomial ring over n variables is equal over a field equals the number of variables. But we will prove that after we develop a little bit about the dimension theory of Noetherian rings. Okay. Okay. So just a few remarks, just one remark. Okay. Maybe I should say 2 remarks before we go on to the next, because we have to slightly digress, develop various things to study dimension more generally. Okay, so let me just make 2 remarks. One, so Krull dimension of Krull dimension corresponds to the notion of dimension for topological spaces to the topological notion of dimension using irreducible subsets. Okay. In other words, a chain of primes in R corresponds to, okay, so let's call it P1, P0 inside P1 inside PL. Okay, so this one corresponds to, okay, V of P0. V of P0 is the smallest, so V of P0 is going to be the largest. Okay, and V of P1, okay, and because P0 is different from P1, this is going to be different because, for example, P1 is inside here but not inside here. Other way around, P0 is inside here but not inside here. Okay, and V of P2, V of PL. Okay, and if you're thinking about rings over finitely generated algebras over algebraically closed fields, then one can also write Z of P1 strictly containing Z of P2, strictly containing Z of P3, and so on. Okay? And these are the irreducible subsets in those topological spaces. So giving a chain of primes is the same thing as giving a chain of irreducible subsets in a topological space. And this is, so Krull dimension is really the notion of topological dimension for Zariski topology. Okay, so that's the first statement. And the second is a small observation about polynomial rings, and we will have to come back to this later. We will have to we'll revisit the problem about dimension of polynomial rings a little later. So just a remark. Sorry, maybe okay, so remark. Okay. Dimension of Rx is at least dimension of R plus 1. X is a variable for every ring R. Okay. This we will prove. It's not very difficult. The point is that if R is Noetherian, then this is actually equality. But in order to prove that, we need to understand more about the dimension of Noetherian rings. Okay, so let's try to give a proof of this. So if P is a prime of R, prime ideal, then its extension is also a prime ideal. Okay. So in other words, it's in the sense that it is not very difficult to check that R, the extended ideal, is really isomorphic to R mod P with X adjoint. Okay. And this is a domain. If you join a variable to a polynomial rings over domains are domains. Are domain. Okay. So therefore, this is a prime ideal. If we take distinct primes inside is a chain of primes in spec in R is a chain in spec R, then P0 extended to Rx. This will be different from P1 extended to Rx, and so on. Okay. PL extended to Rx. Okay. And we can add one more element and make it one larger chain, which is, so let me continue it here. Okay. You take PL extended to Rx and the ideal generated by X. Okay. So one needs to check that the ideal generated by X is not in this extension, okay, and also that this is a prime ideal. So let's quickly check that thing. So Rx mod P Rx comma plus X. Okay. This is isomorphic to, well, we can first kill this and then X, but then this is isomorphic to R mod P adjoint X. Okay. Then its image is X. Okay. This is isomorphic to R mod P. This is true for any ideal. In particular, it's true for prime ideal. So it's a domain if P is inside R is a prime ideal. Okay, so and one needs to check that X is not inside IRX for any proper ideal. Okay. And so that would tell us that this is really a new prime ideal, and here's a chain of length L, here's a chain of length L plus 1. Okay. So therefore, dimension goes up at least by 1, and for Noetherian local rings the dimension is goes up exactly by 1. Okay. So this is Noetherian rings. Okay. So this we will prove after we develop some notion about of dimension. Okay. So the next is therefore what one has to do is to understand is to prove or study the dimension theory of Noetherian Noetherian rings. But if you so note that dimension of R is, so this is as a supremum of chains of primes. So wherever a chain ends at the that is going to contribute to the height of that prime. So this is really supremum of R, dimension of R localized at P in spec R. Okay. So we would like to therefore, so in some sense it is enough to understand a theory of dimension of Noetherian local rings. So let's assume this is a local ring. Okay, so we need to only worry about, so we are interested in Noetherian local rings, and therefore this tells us that it's enough to know for Noetherian local rings. So the dimension theory of Noetherian local rings is done, was developed by Krull and people around that time, and it is done, so one, so there are, so the main theorem it proves that dimension can be determined by as two other numbers. Dimension is equal to some number S and some numbers delta. Okay. We won't call them S and delta, but we'll probably label them later once we get to the theorem. And one of these numbers is obtained by taking filtration of a module. So first of all of this, instead of worrying about dimension of a Noetherian local ring, one can just worry about dimension of a finitely generated module of a Noetherian local ring. Conceptually, proof-wise, there is not any extra difficulty, and some of the arguments are easier to manipulate because one keeps in mind that one is working with modules and not just quotient rings. Okay. So in order to do this, one has to do some filtrations of modules and their quotients, and one needs to understand a little bit about Artinian rings and modules for that. So let's define that. So this is Artinian rings and modules, mostly rings. Okay. We will just define what an Artinian module is, that's all. Definition. An R module, R is any ring, commutative ring now, R module, M is Artinian if it satisfies either of the following equivalent conditions, either or both, either of the following equivalent conditions. One, what is called descending chain condition on submodules. Submodules. So this is abbreviated as descending chain, DCC. What does this say? Every chain M1 descending So it becomes, it gets small, progressively smaller, stabilizes. Okay, so that is, there is some Mn such that thereafter it's equal to Mn. Okay, so analogous to the Artinian, to the Noetherian condition, and to every non-empty collection of submodules of M has a minimal element. Okay, so the proof is exactly the same. So these two conditions are equivalent. So M has to satisfy only one of them, hence it will also satisfy the other. And the proof that these are equivalent is exactly the proof, I mean, it's just reversing the containment and maximal with minimal in the proof for ACC, for Noetherian modules. So I will not prove it in this lecture. So this is what is called Artinian, and definition. R is an Artinian ring if it is an Artinian modulus over itself. Okay. So we'll end this lecture with a strange observation about this kind of rings. Well, it is not strange. It is just, we have not seen this definition so far, so we have not seen that that such things could happen. Okay. Let R be an Artinian ring. Okay. Then every prime ideal is maximal. Okay. So proof. Okay. So let P inside R be a prime ideal. Okay. Then let's consider R mod P. Okay. So if R is Artinian, then a descending chain condition will also hold for R mod P. A descending chain inside R mod, so here it would mean descending chain of ideals. So a descending chain of ideals in R mod P lift to a descending chain of ideals in R, and if that stabilizes, it will stabilize inside R mod P also, or any quotient of other matter. So R mod P is Artinian. Okay. Suppose it is not a field. Okay. Let R be inside R, R not 0, R not invertible. Okay. Then the chain R square, R cube, so these R square is inside R, so it is inside, R cube is inside R square and so on, so it is strictly descending. Okay, that is, if not, there exists some R, there exists N such that Rn is same thing as Rn plus 1. Okay, what does that mean? It means that Rn, there exists some A such that Rn is of the form A times Rn plus 1. Okay. Now, this implies that Rn times 1 plus AR, 1 minus AR is 0. Okay. But this is a domain. We are working with R mod P. Okay. R is a domain oh sorry, what did we say? Sorry, let's just take inside R mod. I didn't change notation, so we're talking about R mod P. Since R mod P is a domain, we'll get that 1 minus AR is 0, or in other words, we get AR equals 1. That is, R is invertible, but that we assume it was not invertible. This is a contradiction. So this contradicts the this if not part. So it is strictly descending. Therefore, R is not Artinian. R mod P is not Artinian. This is a contradiction. This contradicts the assumption that R mod P is this. Okay. So let's take some quick look at examples. Fields Z mod n, where n is non-zero. Okay. Same argument, P kx mod some fx, k field f naught 0. Okay. So these are all Artinian rings. Z is not Artinian for the same argument as what we just showed in the proof. PIDs, nothing, Z PIDs, polynomial rings, they are not in larger number of variables, they are not Artinian. So this is the end of this lecture. In the next lecture, we will continue studying the structure of Artinian rings.